Okay, I've put problem set 7 up, so it's 13 questions. It covers things late in the story of airflow, the balls in air and airplanes, and then it goes on into the topic for today, which is wood stoves. So it's due next Wednesday. So current topic story is about how wood stoves work. And I'll actually start off with a question. Try this one. So which is more effective at heating a room? And you get two choices of wood stove or their equivalent. You okay with the question? Basically, does the color matter? So I'll give you 30 seconds, and then we can talk about the answer as preview to the story. 5, 4, 3, 2, 1, blink. Get a slight majority going for the black wood stove. And that's actually true, okay? So the black wood stove is a better choice. There's a reason, I mean, okay, gold costs something, but there's a choice, there's a reason why most wood stoves are dark, are black. And the answer has to do with the process of sending heat out into the room, which is a major topic for now and for the next couple topics. That if you want to send heat out into the room, we'll have to talk about what is heat a little bit. And if you want to send it out, you want to use the 3 classic ways in which you can send heat from one place to another, from one object to another. They are conduction, convection, and radiation. And the issue here is radiation. That if you want to pass heat from a wood stove to objects in the room by radiation, which is light and light's near relatives, it actually comes best from a black object. Oddly enough, black objects emit thermal radiation better than anything else, and in particular better than shiny things. Gold shiny is especially bad at emitting the thermal radiation that the wood stove emits. So that's equivalent of wrapping the wood stove in an insulating pad. Makes it really tough for the wood stove to send its thermal radiation out into the world. And so my goal for today is to talk first about how the wood stove creates the thermal energy that ultimately becomes the thermal radiation, and then how it, or the heat that flows out into the room in general, and then talk about how it flows out into the room in general. So that's my goal. You can send me messages again. I got it, I rewrote the thing and it works. So you can send me notes, one of which came in sometime in the past asking, what happens when an unstoppable force meets an immovable object? And there you get an example of something that's not possible. Used in common language, but there is no such thing as an unstoppable force or an immovable object. Everything can move, and there are no sort of infinite forces. So all these potential infinities. There's no infinite mass, which would be an unmovable object. And there's no infinite force, which would be an irresistible force. So, okay, anyway, do ask questions. And since it's an intimate gathering today, we can talk about some of the applications of the whole story of heat flow from object to object. In particular, I used to ask in a problem set the story of cooking, particularly cooking in an oven. But let's just walk all over that today anyway. You all ought to know how cooking works in an oven and why there are various choices for how you do the cooking. Okay, so let me get this out of here and talk for a second. First off, so in a wood stove, I mean, the basic story is you put wood in it, you ignite the wood, it burns, whatever that is, and gets really hot inside there, and the really hot inside there ultimately drifts out into the room and warms everything up. And as we're going to colder weather, this is something that might be appealing, certainly more appealing than it was in July. So what's the story of burning wood? So issue number one, you're starting with ordered energy. When you put the wood into the stove as is, the energy is an ordered form. That is a form that is essentially equivalent to work. I've used that term cavalierly and just make sure everybody's on board with it. When I say it's equivalent to work, which is a physics jargon statement, it means that with the right equipment, you could take the energy from some sort of potential form, in this case, and you could convert it into work done on, I don't know, push something and have it move a distance in the direction of that push. It can do work directly. Thermal energy can't do that. Thermal energy is all chopped up into little bitties. It is not equivalent to work. So you could have 100 units of energy. The classic unit of energy is the joule. You have 100 units of chemical potential energy that's equivalent to work, and you can also have 100 joules of thermal energy that's no longer equivalent to work. It's been chopped up into bitties, and it's now hard to get it to do work. In fact, it seems hopeless, but we'll discover in a week or two that you can still get thermal energy to do work if the situation is good. Specifically, if you've got two different objects at different temperatures. Okay, so back to the wood. The wood's got chemical potential energy. What does that mean? It means that if you go look at down, zoom in with some super microscope down to where you can see atoms and molecules, you will discover that atoms and molecules interact with each other. They exert forces on each other, and the forces ultimately they have to do with electricity and magnetism. They're the forces between charges and magnets and stuff like that, which we're not doing this semester. But you can just sort of blur that over and make the following observation. That if you've got two atoms, so these are two atoms, we won't worry about the parts in them. That's also for some other year. You've got two atoms at great distance from each other. They exert no force on each other. They're oblivious to each other. And that's sort of life in a gas. The atoms are bouncing around. But if you bring them closer together, they start to exert forces on each other. Initially, the forces are attractive, meaning that as I bring them together, suppose I'm holding them with tweezers, and I'm bringing them closer and closer, at some distance, maybe about here. We're super zoomed in, so I don't know how far is this separation. It's pretty small, of course. They begin to attract each other. And because they're attracting each other, I have to hold them back with my tweezers. Otherwise, they'll jump. Okay? So they begin to attract each other. So they're pulling my tweezers together, dragging them closer and closer and closer. And during this period of time, they're doing work on me. Okay? So I'm getting energy out of them. They get closer and closer, and eventually they sort of effectively touch, at which point the force goes from attractive to zero. So let me unwind back to here, and then so the force gets stronger, 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 strongest. The peak force, now it's getting weaker and weaker, 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 and now, because they're starting to overlap, and now it hits zero. And if they go closer still, it actually becomes repulsive, meaning that they don't like each other, they push apart. So during a bounce, if you let two atoms come together and bounce, which they will do happily, they'll speed up faster, faster, faster. They will hit maximum speed right at that equilibrium. It's the same old story, approximately. They hit equilibrium at peak speed, and they coast through it, and they get too close, they repel, they bounce off each other, they go back to equilibrium at peak speed, and they fly right back apart. So this is how atoms bounce, and they're doing it in this room all over the place. They do it during the near approach. They're actually pulling together, then they're pushing apart. Now off they go. So where's the chemical potential energy in this? Suppose I had two oxygen atoms, and I bring those oxygen atoms closer and closer. I'll stick with oxygen. It's good. Closer and closer. they're pulling together, they're doing work on me as I do this, right? They're pulling together and I'm holding them back so that they can't go faster. They reach equilibrium and I set them down and they walk away. I've stolen their energy, right? They did work on me in the process of coming together. I've got that energy. They don't. Ha ha, they're stuck. They are now chemically bonded to one another, which, what's a chemical bond? A chemical bond is a deficit of energy. They need that energy back to come apart again. They gave it to me, I took it, and now they're running a short. They can't come apart until somebody pays that energy back. So I can come in here and I can pull them apart, an action which requires me doing work back on them to yank them apart against that attractive force, and now they're back to where they were. But I would say all the oxygen atoms in this room there are no free oxygen atoms in this room, no free nitrogens. It's a little overstatement, there are probably a couple. But basically, they have all paired up. Two nitrogen atoms, shunk, they pull together, they stick, and if something takes away their energy while they're in contact, they're stuck. They're bonded together. So the point is that a lot of atoms and molecules, a lot of atoms are bonded together just when you find them. This room is full of nitrogen pairs, oxygen pairs, and zillions of more complicated molecules in you, for example. They're held together by that deficit of energy that came about during the process of assembling when something stole the energy and walked away with it. We okay with this idea so far? Wouldn't thermal energy do work on a hot air balloon? The answer is actually yes. If you heat the balloon up and it rises, it can do work on you. So the energy will be coming to you as work, and this is going to be, where's it going to come from? It's going to come from the difference in temperature probably between inside the balloon and outside the balloon, which is where the order shows up that allows you to get some energy out of thermal energy. If you've got things at different temperatures, you can get some energy out of it. So that's actually an interesting observation that a hot air balloon pulls it off. Can you explain how you do work on atoms? Well, if atoms weren't so small, you could in principle hold them with tweezers. And the act of gripping them with tweezers doesn't involve any work. You just got to tie a string to them, glue it on. Now, if you've got something with which you can hold them back, as they pull together, they are pulling toward each other, and you are holding them back. As you go closer and closer, your force on them is outward, right? So they don't go together. Their force on themselves, on each other, is together. They are doing work on you. It's like holding. Oh, the obvious example comes to my mind is you got two dogs on leashes. Each dog, you name them. Call one of them nitrogen, the other one oxygen. I don't know. No, hydrogen. There. Here you got them on leashes, and they're attracted toward each other. Right? They're going to go and woof at each other. So if you sort of hold the dog back because it's going towards the other dog, it's doing work on you. It's giving you energy. And I'll leave the dog analogy back, because it's going to get in trouble. Pretty soon they're going to be. All right. So as they're going together and they're doing work on you, you can take that work and walk away, right? You remove the tweezers. They're stuck. They're stuck by virtue of an energy deficit that would have to be paid back to pull them apart. Other questions about that? All right. Yeah, it's similar to Newton's first law. I'm not sure where that applies here. If you want another analogy that's probably more practical, is two magnets oriented so that they attract. If you want to keep them from jumping at each other, you have to hold them back. They'll do work on you. They'll come gracefully to the point where they're touching each other, and then you walk away. They're not going to come apart unless somebody comes back and pulls them apart as they move apart. In other words, does work on them to drag them apart. So they're held together by an energy deficit again. Okay? The energy deficits that show up when in different pairings or trios or quartets as all the molecules are assembled. The amount of energy deficit in a particular molecule, and a molecule is just an assembly of atoms held together by these energy deficit chemical bonds. If you look at a particular molecule, it's going to have a particular energy deficit, grand total, and the parts will have their own sort of local energy deficit. Like there may be parts of a molecule that come off easily and other parts that don't. So one might take 1 unit of energy to pull it off, another one might take 6 units of energy, and so on. So if you look at the molecules that are in this room, and you look at the molecules that are in wood, they're assembled and they have their energy deficit, but if you rearrange them, if you took all the constituents, for example, the oxygen atoms that are in the air, and the carbon atoms that are in the wood, among other things, and you rearrange them, you could get a bigger energy deficit. That is, you can get stronger bonds overall. They would take more energy to pull them apart, and you could get them to release energy, whether it's as work or as heat or as thermal energy, we'll see. So that's what happens. 2 cents about wood, just because it's a wood stove. Wood is actually made of the most common plastic on Earth, which is cellulose. Cellulose is a naturally occurring plastic. What do I mean by plastic? It is what's known as a polymer molecule. It's assembled out of repeating units, little pieces that are repeated and that are bonded to each other, and they repeat over and over and over and over. So it's like a long chain or structure built out of the little basic building blocks over and over and over, like the stack of Legos 1,000 billion, hugely long. The little units that are assembled, they're sugars. They're sugar molecules. There are a variety of different sugars around. But if you stick 2 of them together, you can end up with like sucrose, which is like cane sugar, standard classic table sugar. If you start stacking more and more of them together, you can end up with cellulose. Cotton is almost pure cellulose. Wood is a significant fraction of its cellulose. It's got some other stuff in there. So most plant materials, the cell walls of plants are built of cellulose. That's their favorite building block. So there are zillions of tons of cellulose on Earth, and it's all sugars. If you eat it, it doesn't do you much good. So eating a cardboard box is not very helpful, even though you're eating mostly cellulose, or a big blob of cotton, because we don't have the wherewithal to break apart the sugars. Even cows don't themselves, but they have microorganisms inside that do. So and I think horses have enzymes that can do it. So they basically have the ways of taking apart the sugars such that they can digest it. So we can't digest cellulose. There's a slight rearrangement, a variation on cellulose that is digestible to us. It's called starch. So starches, they're also these polymer structures. However, they're assembled in a way that we are capable of disassembling and getting nutrition out of. So starch, you get calories from starch, no calories from classic fiber, which is cellulose. Okay? Fun facts. All right. So if you disassemble cellulose and air and then reassemble it in a new way, you can get stronger chemical bonds. That is, which is to say, you can end up with a bigger energy deficit after you've done the reassembly than you had before you did the reassembly. Where does that energy show up? Typically as thermal energy. So when you're burning cellulose in air, the oxygen molecules in the air, the cellulose molecules in the wood are rearranging and reassembling, and they come out typically, the vast majority of them come out as water and carbon dioxide. The same atoms and molecules went in, rearranged, and out comes water and carbon dioxide, which are very tightly bound structures and takes a lot of energy, relatively speaking, to tear them back apart. Okay? That's burning. For most burning, I mean, you can burn other things, but that's what's going on in a wood stove, that rearrangement. To get it started, so it doesn't just happen spontaneously, which is to say you put a chunk of wood, there are plenty. This chunk of wood here, the oxygen in the air, why aren't they rearranging and doing this trick I just described? And the reason is because to get that rearrangement to occur, something's got to start the disassembly process. Like you have to pull the oxygen, the pair of oxygen atoms that are in an ordinary oxygen molecule. You have to pull one of the oxygens off, which costs energy, and then stick it onto the carbon, for example, that's part of the cellulose molecule. So the rearrangement, overall, it will pay off beautifully. It'll release lots of stored energy, which is potential energy. However, you have to pay up front to get the rearrangement to start. Hope that's not surprising. Chemists call that an activation energy, that you want to have the chemical reaction occur, and these are all chemical reactions. You want to get it to occur, you got to pay up front with a certain amount of energy to sort of get the structures coming apart, maybe not entirely, but partly apart, so that they can rearrange. And that activation energy isn't available at ordinary room temperature. So at room temperature, everything's got, things are jiggling around with thermal energy. But the amount of thermal energy in any particular atom or molecule and its pieces is governed by statistics and the local temperature. It's governed by statistics in that the jiggling process involves a lot of randomness. And so if you go looking at one instant in time, you take a flash photograph and you go and look at all the atoms and molecules, say in a piece of wood, you'll find some of them moving faster than they should, and therefore having more kinetic energy than they should. And some of them moving slower than they should, meaning they have less kinetic energy than they should. But the statistics if you take the statistics of a lot of those atoms and molecules, you'll discover that they're very well defined, and the extent to which they can deviate from the average is also very well defined, and they just can't. No atoms and molecules in the world are going to have so much energy at room temperature just by sheer accident and statistics that they can undergo the rearrangements. So if you want to get wood and oxygen to burn, you got to raise the temperature. You've got to statistically give the atoms and molecules more energy. It's just their random motion before they will eventually get to the point where you get hot enough, eventually they can rearrange. And that's sort of an ignition temperature. Why do you have to hold a match to the piece of wood? You need that initial thermal energy and the elevated temperature to pay those initial activation energies and get the process going. And eventually it'll become self-sustaining. It releases enough thermal energy itself to cause more rearrangements and cause more rearrangements and more, and the burning then becomes self-sustaining. So that's what you're doing when you're lighting the fire. You're putting in thermal energy, raising the local temperature to the point where there's enough energy around in the random motions to start paying these activation energies and trigger the rearrangements, the overall chemical reactions. What's the difference between heat and thermal energy? Back in the day, I walked right over the difference. There is no, it's the same. Okay, that was my naive opinion. The purists distinguish. Here's the story. Objects contain thermal energy, but when the thermal energy moves from one object to another, because of the difference in temperature, that moving thermal energy, that's heat. Okay, so you don't contain heat. Heat is thermal energy on the move. Do I care about that distinction very much? No, but it's there are people who do, and I live with that. Is that okay? So, when you burn the fuel in the stove, you are taking chemical potential energy, which we can track back into the distant past. You could track it all the way back to the sun, because where did the chemical potential energy come from? It came from the sun that caused the plant to grow, rearrange molecules, build these cellulose structures and stuff, and then you cut the wood down and put it in the stove and so on. That chemical potential energy, when you ignite the wood, when you add enough energy to pay that initial activation energy and get the combustion going, it becomes thermal energy. So this inside the stove gets hot. As it accumulates more and more thermal energy without accumulating much more mass, its temperature goes up. Okay? 2 cents about temperature. Temperature, you certainly have a sense of what temperature is by empirical sense. You encounter temperature all your life. To a scientist, finally, looking at the origins of this whole notion of temperature, it has the following definition. It is the average thermal kinetic energy per particle. And I'm going to hesitate on the word particle because that's not quite the right word, but it's good enough. So if you have a baseball here, the temperature of the baseball determines, if you look at all the little particles that are in there jittering around, they have a mixture of kinetic energy that's in their motion and potential energies as they bump into each other, for example, or as they cling to each other. So set aside the potential energy. That's not part of temperature. It's the kinetic energy that we care about. And if you look at the average, this guy's going this fast, it's got that much mass, therefore it's got a certain amount of kinetic energy. This one's got that much kinetic energy, that one. You average over it, and that determines the temperature. There is a direct relationship between the kinetic energy per particle and the temperature. If you double one, you double the other. The constant that relates them is beyond what we want to talk about. Okay? So as you turn up the temperature in the wood stove, every particle's got more and more thermal kinetic energy. The word thermal's in there because the kinetic energy, this kinetic energy, the whole thing moving, doesn't count. It's the little local motions that we care about, the thermal motions. All right, so that's burning in a wood stove. Any question about burning in a wood stove? Then I can just leave that behind and look at getting that heat out into the room. And this is where, from my perspective, most of the action is. There are 3 classic ways in which heat goes out into the room. One of them is by conduction, which is heat moving through a material without the material itself moving. So, and I'll say them, and then we'll play games. So, when you, when I take a metal rod, poker, you put the poker, and for some reason they made the poker not out of cast iron, but they made it out of copper or aluminum. Bad choice. You put it in the fire and start poking the fire around. Pretty soon it gets too hot to handle. Heat, again, now this is thermal energy on the move, has moved from the hot fire end of the poker to the cold, you're holding it end of the poker, and burned your hand. So that's heat moving through the material by the phenomenon known as conduction. Second way in which heat can flow around is convection. I mean, you hear about this stuff in K through 12. You surely have heard these words and all that stuff. It's kind of amazing that this is really it. These 3 really are the ways in which the heat flows. So convection is heat moving within a mobile material like a fluid. So if you heat up air down here, we've seen you heat up air, it expands. If its pressure doesn't change, which meaning that it's exposed to atmospheric pressures, so you're going to heat the air, but it's going to still be the atmospheric pressure. For it to be hotter and at atmospheric pressure, it's got to be low density. The molecules get farther apart. It's now light, fluffy stuff, and the buoyant force exerted on it by everything else is more than its weight, and up it goes. So the heat is now moving in the material as the material moves. Okay, so that's convection. And the third one is radiation, which that one you've heard about way back whenever. That's more mysterious. What the heck is the thermal radiation? And we'll do that one carefully. Just as a more preview, the radiation we're talking about, and radiation is an overused word that's a catch-all for sort of anything that's moving. This is baseball radiation, okay? So the radiation we're talking about here is electromagnetic. It's light. and radio waves and microwaves, they're all very closely related phenomena. They're all the same phenomena that varies only in the details quantitatively. All right? So, conduction, convection, radiation. Fun and games with conduction. So, what this is, can I figure out? One of these is aluminum, and one of these is stainless steel. I think that's aluminum. Okay, what I'm going to do is I'm going to light the burner here. And I can light it now, talk about it while it's going. Okay. I'm heating the central hub of this gadget that has 3 spokes on it. And the 3 spokes are made of different metals. This is copper, that is aluminum, and that's stainless steel. And they have different abilities to carry heat by convection. Conduction. Think before I talk. Not always good at that. They conduct heat with different abilities. And copper is going to be the best, aluminum's second, stainless steel is terrible. It's going to be way third. So what you're going to see as time goes on here is heat is going to flow from the hot hub out these colder spokes. This is room temperature out here. And as it goes out there, it's going to melt the waxy, putty stuff that's holding up the metal marbles. And they'll fall. And sometimes one of them falls off for no good reason. But basically, here's what's going to happen. The heat is going to flow out the copper most successfully. That marble should be the first to fall. And certainly, this marble here at the end is going to be the first end marble to drop. Aluminum is going to do a decent job. Not as good as copper, but pretty good. So it'll be second in the race. And stainless steel is going to be completely terrible. It doesn't conduct heat well at all. And for the purpose, so aluminum beat copper, but sometimes, copper was close. By the time they get out towards the end, copper's going to win. All right? So this is showing the thermal conductivity of these different metals. So different materials have different thermal conductivities. So there is a good definition for what thermal conductivity is, and people measure the thermal conductivities of all the different materials you can think of. So I'll just give you some general rules of thumb. See, copper's starting to really pull out into the lead here. First rule of thumb is the metals conduct heat better than the insulators, with exceptions. What's a metal? A metal is a material that has electrons, that can conduct electricity. And how does it conduct electricity? Electrons, remember about electrons, so I'll pull them in here. So aluminum now. Electrons are the little particles on the outside of atoms that make up the outsides of atoms. Okay? And they are also the main carrier of electricity in metals. That is, they can move from atom to atom. In fact, they can move long distances in metals. And they're relatively mobile in metals. So you think of electrons as belonging to individual atoms. That's no longer true when you assemble metals together, metal atoms together to make a metal. The electrons are mobile. They go long distances. And that makes a big difference for electricity, because, of course, now you've got something that's able to carry electricity with the help of the electrons, which carry electric charge. But those electrons can also carry thermal energy. And to see how that works, the thermal energy moving through, say, a piece of glass or through water. Okay, copper's done. And you can see what stainless steel is doing. Nothing. And I'll bring this to practical uses shortly. When thermal energy is being conducted through, say, a piece of glass, it's going atom by atom by atom by atom through the structure. This atom is jiggling a little harder, it nudges its neighbor. That one is jiggling a little harder, it nudges its neighbor. It's kind of a bucket brigade process. It goes through every single atom all the way across the material. It's a very tedious, slow process to get the heat to flow through. It flows from hot to cold. Why? In this process, it's a statistical story. That if you've got one end of the glass with everybody jiggling hard, aluminum finally caught up. and the other end jiggling gently. That's the hot end, this is the cold end. Statistically, the jiggling motion is going to work its way down the system. It's not like the guys jiggling gently are going to jiggle even more gently. That's just so unlikely. Their environment over towards toward the left, is all more vigorous jiggling. It's going to infect this group down here that's not jiggling hard. So the cold end does not get colder. It's just wildly unlikely. Instead, it starts accumulating some of the thermal energy from the hot end. And it's driven by statistics. And so eventually you end up everybody the same temperature. So the heat's flowing from the hot hub to the colder ends because of statistics. If those were glass rods, it would go atom by atom by atom all the way through. It's not going atom by atom by atom in the metals. Why? Because the electrons can move from one atom past 1,000 atoms to one down there far, far away. And those electrons can carry thermal energy with them. You get the electron moving vigorously, it zips across vast fields of atoms and transfers its energy to a distant atom. So it skips the whole bucket brigade process. And basically, the better the electrical conductor is, that is, the more mobile electrons are, and the more of them there are that are free to roam, the better it carries thermal energy too. You okay with that idea a bit, or questions about that? Anybody here? Yeah, nope. So, good electrical conductors are also good thermal conductors, with exceptions. And insulators are typically not very good thermal conductors, again, with exceptions. So where does this matter? If you're buying pots for your stove, so I said I'd talk about cooking. Suppose you're going to cook stuff on the stove with a pot. What materials do you want the pot made of? Well, two problems that I can think of that occur in pots, if you just buy random pots, particularly cheap pots. One is that it doesn't move heat around well in the pot itself, and therefore if you heat the pot imperfectly, you heat one side of the pot, not the other, you burn food on that side of the pot, and you leave the food on the far side of the pot uncooked, right? The heat, one part gets hot, the other part doesn't get hot. There's no tendency for heat to flow from hot to cold because it's a terrible conductor. You're not going to cook evenly, I mean, the bottom line, okay? So when does this happen? Well, this happens if you buy a really thin stainless steel pot. Why? You can see stainless steel is a terrible conductor of heat. Incidentally, why is it a terrible conductor of heat? It's an alloy made of all kinds, several different metals. It's primarily still iron, but it has a lot of chromium and nickel in it. And the result is that its microscopic structure is very complicated and disorderly. And as a result, electrons trying to go through this are going through this mishmash, and they don't go very far. And so it's the fact that it's a mishmash of metals that make it not a very good electrical conductor and not a very good thermal conductor. It's great as far as avoiding rust and avoiding stains and all that stuff. So it's lovely as the outside surface of cookware, but it's crummy for moving heat around. And so if you get a thin stainless steel pot, it's just 100% stainless steel, you can heat one side of it red hot and leave the other side still cold. I don't know, do I have any such things? I do. So here's some stainless steel. So this is stainless steel. Actually, it's a tube, which is a little bit of a cheat. If it were a rod, I might get a little warm here. But I should be able to heat this thing cherry red while I'm holding the other end. I would not do this with copper. Okay? So, general rule, don't buy a stainless steel pot that's just thin stainless steel in the cook part. Another thing with pots, another issue with pots, is sometimes you burn your hand on the handle. So if they make the handle out of copper, you're in trouble. So they make the handle out of stainless steel, and now you're good. If it's pure stainless steel, you can get the pot as hot as you like, and you will keep your hand cool. Do you see that it's cherry red? Is it glowing for you? So, all right. I'm not going to do that with copper. Okay, I've got a few more things to do here. So, what's the alternative to a thin stainless steel pot? Well, don't use stainless steel in the pot. Use something that's a good conductor of heat, copper or aluminum. Copper has the problem that it corrodes, and also it's toxic. So pots that are entirely copper, particularly on the inside, you got to be a little careful what you cook in them, otherwise you're going to be consuming some amount of copper. Aluminum's safer, but you can get it dirty fairly easily. So some of the best modern cookware is laminated. Put the good conductor of heat, namely aluminum or copper, inside a veneer of stainless steel. Don't count on the stainless steel to conduct heat. Let the aluminum or copper do it, but use the stainless steel as a coating to give you a pretty, non-corroding, clean cooking surface. Is that okay with everybody? You'll see these pots, you've probably used some of these pots. I don't know, maybe none of you cook anymore. But if you do cook, pay attention to the construction of the pot itself. You want high thermal conductivity in the bottom and low thermal conductivity in the handle and maybe a corrosion resistant outside. Okay? Before I walk too far away from this, fun and games, right? One thing you ought to see is what happens to certain materials as temperature changes. I mean, obviously they can start glowing red hot, which is thermal radiation will come to, but they can change their behaviors in interesting ways. I can't justify why this is exactly part of the story, but this is a lead bell. And you all know about, or many of you at least know about the Liberty Bell. What does the Liberty Bell have that was, I can't do this a question. It's got a crack, right? Making bells was a very hard job because you needed to make it out of a metal that was very hard and stored energy well. We'll talk about clocks and things down the road, musical instruments. Musical instruments need to be able to go through a motion as a they need to be able to go through a rhythmic motion over and over and over and over again, many, many times, without losing energy. Lead doesn't do that. Most metals don't do that. Bell metals do, but bell metals are very hard, very difficult to work with, and up until recently, lots of bells have been cast over the years, and many of them have broken because they're trying to make, the constraints are terrible on what makes a good bell. One cheap approach is to go cold. So a lead bell, it had no tone, if you noticed, when it was at room temperature. But if I cool it to liquid nitrogen temperature, I harden it. I'm removing the thermal motion, and it becomes mechanically very hard, like a crystal goblet, which you thwack a cheap glass and there's very little tone. There's a little tone there, but crystal, it's great. So if you're willing to liquid nitrogen cool your bells, you can make them out of almost anything. At room temperature, not so much. Okay? Fun and games. All right, I just can turn this off. Stainless steel, forget it. Okay? Not good thermal conductor. I'll leave thermal conductivity and go to the next mechanism for moving heat around the room. So I should say, in the context of a wood stove, thermal conductivity carries heat from the firebox through the walls of the stove to the surface of the stove. So we can easily get the thermal energy and heat on the heat itself. Heat coming through the walls of the wood stove. Typically, it's made out of metal. If they made the wood stove out of ceramics, depending on ceramics, not so good. Ceramics, you can get ceramics pretty hot while holding them too. They don't conduct heat well. It depends on which one you choose and how you make it. But basically, a metal firebox is the ideal for a wood stove. Now, how do you get the thermal energy into the room? Two mechanisms left, convection and radiation. So what's the story of convection? If you heat a fluid and then move the fluid around, the heated fluid can carry heat. And that's convection. And there is what's known as natural convection, and that's what I'm going to show you first here. There. What you're looking at on that screen is this little box here, right? Hi. There's an electric heating element in water. And when I run an electric current through that heating element, it's going to get hot. And it will heat the local water, and you'll see what happens. I'm doing it now. So the local water is being heated. It's making bubbles to some extent, which is cheating and not the story. But the water will begin to rise off that heating element. The question is whether we can see it go. I don't know if you can see the actual streams of heated water rising. That's self-defeating. Can you see it? No, I don't have any. Was that good? Okay. Good. Oh, there you go. Okay. Now you can see the shimmering heat coming off, and with it the rising fluid, at least to some extent. We do this normally with a projector, and the projector definitely gives you the appearance of rising fluid, but that's what I'm trying to give you. So the point being that in a wood stove, the hot surface is heating the air, in fact, by conduction, right to the air that touches it. And then that hot air becomes buoyant, and it rises to the ceiling. It rises to the ceiling, it spreads out, it actually makes cells, what are called convection cells, where it rises up, spreads out on the surface, cools, and then it descends back to where it started. And it loops over and over. And that's what's happening around a wood stove, is that you're getting these convection cells coming off it. You know this from experience on a wood stove or the burner of a normal stove. You put your hand over it, you feel the stream of heated air coming at you, right? And the hottest place to be is like right above the stove, which is where no one is. If you're really cold and you want to be warmed up quickly, you want to stand over the stove. Alternatively, don't rely entirely on natural convection. So this is natural convection. It's driven by buoyancy. Hot air rises, cold air descends. You can also force the convection by putting a fan in the room, a ceiling fan or a fan beside the stove. Churn the air yourself. When you do that, it'll still be heated. The air will still get heated in contact with the stove, and then it will go somewhere else. It'll be driven not by buoyancy, but by the fan. All right? And that's maybe good if you've got a tall ceiling. If you've got a wood stove and the ceiling of the room is very high, the hot air is going to be up there in the ceiling. You want to get it down here? Blow it down here with a ceiling fan. In the context of cooking, that means that instead of cooking typically when you're baking something, you have a heating element of some sort at the bottom of the oven. And hot air heated down there rises, goes up, and cooks the food. Because of natural buoyancy, it rises, it spreads out, cooks the food, cools, descends, goes back, and gets more heat over and over. But you can do better if you put the fan in. So that's what a so-called convection oven. It's not a convection oven. Every oven's a convection oven. What a convection oven is, a forced convection oven. It's stirring the air deliberately with a fan. And now you don't wait around for wimpy buoyancy to do the job. You churn the air yourself. And now that hot air picks up heat at the heating element, moves to the food, drops it off, goes back to pick up more. So forced convection ovens are much more effective at cooking than ones that rely on good old-fashioned buoyancy. All right, so we've gone to the hour, and I'll continue on Monday with radiation and what it's like to broil food.